So I will just speak about curves and how to parameterize them in a appropriate way, depending on applications, and eventually decrease the number of points necessary to accurately sample a curve. So you all know, I suppose. So I will give a motivation from medical imaging, and I will speak about geometric invariance of curves and canonical parameterizations. So let me start with a motivation, which is a research on rheumatoid arthritis, which is a autoimmune disorder. Actually, it's a disease that affects the joints and is very painful. And to quantify this disease, we need to have So first of all, the images I will use here, it's based on a study by Georg Langs from University of Vienna, from the medical university. So he was quantifying this disease, and he concentrated on the spaces between. So here is an X-ray of two hands. So that's a modality that is used in this application. And there are two main consequences of this disease. There is erosion and joint space shrinking. So here in this setting, we are just interested in this joint space shrinking. And the way that people compute it is the following. They put landmarks around the bones, and then they select landmarks that are located between, so in this joint space, and then they add the distances between the landmarks. So here is you see the different distances between corresponding landmarks, and this gives you a value that is then interpretable by the medical staff to follow the increase of the disease. So this is in the very early stage of the disease, because then there is a lot of erosion and you cannot define this very properly. Anyway, the way the university or the hospital in Vienna is doing it, they are using an algorithm coded by Todberg, who places the landmark in a way that are geometrically meaningful. So it's always the same number, the same indices of the landmark at the same position. But there is some variability, of course, between patient and bones. So the aim is to have the same index of the landmark at the same position across the different size of bones and geometry of bones. So these landmarks have to be placed at the same anatomical positions, and this position have a geometrical characterization, and it's depending on the curvature of the curve, which is a contour of the bone. So to do it in an automatic way, we propose to investigate curvature-dependent parameterization of the contour of the bones. So that was the motivation to introduce other parameterization of curves than, for instance, arc lengths. So let me recap what the curvature of a plane curve is. So you can start with a curve. So here it's the face of El Cartan. If you look at the contour, it's this red curve. You can parameterize it by arc lengths, and you can compute the sine curvature, which is the rate of turning angle of the velocity vector when you follow the curve. In 2D, it has a sign, so you know when you turn left and right, basically. So for instance, if you look at the mustache here, there is in blue the maximum of the sine curvature, in green the minimal of the sine curvature. And basically the curvature, if you look at the glasses of Elie Cartan, here you see the circle that approximates the best the curve in blue, and the curvature at this point will be the inverse of the radius of this circle. So this is based on moving frame along the curve. So the curvature function, the curvature that you measure like this gives you a function around the contour. So in arc length parameterization, you have the top function here. If you change parameterization, I will particularly define the curvature length parameterization or curve arc length parameterization. This curvature function will just spread, deform a bit. It has the same variation, but not for the same parameters. So you see the difference so this is, in the second line, for instance, you change the space, the parameter space of your curvature function. So for instance, here you see that you will take more parameters for the part of the curve where there's a lot of curvature. This is the idea. So we will see in a moment. So what is arc length parameterization? That's actually you can resample any curve using arc lengths, using some interpolation of the curve. So for instance, here we start with a Statue of Liberty with sampled by some points, not uniformly, and using here it was a spline in MATLAB. You can approximate a function that go through these points and resample it uniformly. So this will be the discrete version of a uniform or arc length parameterized curve. Of course, you can also reconstruct the curve. That's a very important point. Just from the curvature function, if you know the length of the curve, so you know exactly how many points you have. So exactly the distance between two different samples. And the curvature function will give you the turning angle between two segments. So you can really reconstruct the curve with these two informations. The reconstruction here is the last picture. It's not perfect. If you see the upper part here where the flame is located, there is a bit of deviation which comes from the error of reconstructing the curve from curvature. So if you look at it mathematically, so here we were interested in length one curves, but it's more general than that. If you take the space of curves and then inside the space of parameterized curves, and inside the space the space of arc length parameterized curve. This arc length parameterized curve is a submanifold, and you can project on it, and this is exactly what you're doing when you're reparametrizing a curve by arc lengths. You're taking a arbitrary parameterization and you project on this submanifold of arc lengths. So this projection actually is a smooth retraction from the ambient manifold of parameterized curve onto the submanifold of arc length parameterized curve. And also the space of arc length parameterized curve is diffeomorphic to the quotient of the space of all parameterized curve modulo the reparameterization group, which is, in this case, is a group of diffeomorphism of your parameter domain. to prove this kind of so I didn't mention, I should have. Yeah, this result is in collaboration with Steve Preston, and to prove this very natural and easy result, we need Nash model inverse theorem, because we are in the Fréchet setting, so it's a bit non-trivial. Anyway, let me define the curvature length parameterization. So, as I said, arc length parameterization is used to compute the curvature function, and then when you have it, you can integrate the absolute value of the curvature along the curve, and so you have this total integral of the absolute value of the curvature, and then if you renormalize this is the integration of the curvature along the curve. So for instance, there is a big step here when you're at the level of the mustache. And so you integrate the absolute value along the curve, and you divide by the total curvature in order to be between 0 or 1. 0 or 1 is the space of my parameter. So for t equal to 0, I'm at the starting point, and for t equal to 1, I have made the loop along the contour, and I'm back to the starting point. So here, what you get by integrating the absolute value of the curvature is a strictly increasing function from 0,1 to 0,1, so it's a diffeomorphism. And you can use this diffeomorphism to reparameterize your curve. And this is exactly what you obtain if you use this diffeomorphism, is a new parameterization of your curve, which put the points exactly where there is a lot of curvature. Because if you look, so here we sample actually uniformly the output of this function, and this will put a lot of points where the curve is steep, and the curve is steep exactly where there is a lot of curvature. So here we put a lot of sample in the very interesting area where something happening in the contour. So here in the mustache, for instance, there is a lot of points concentrated here at this part of the curve. On the other hand, where the curve is flat, for instance, if you see here, there is a flat piece, there's no point at all. No point at the flat pieces, which may be a problem actually if you look at the example of the Statue of Liberty, because there is this part here which is completely straight. Curvature length parameterization will put no point there. And also you cannot reconstruct the curve only with the information of the curvature. You also need to know how long are these flat segments. So that's why I proposed another parameterization, which is curve arc length, which is exactly a mixture between arc length and curvature length. And here what you see is you can interpolate between curvature parameterization, where you put points where the curvature is maximum, and absolutely no points on the straight lines. And at the other hand, you have here arc length parameterization, where the number of points is, where the points are uniformly distributed. And you can interpolate between the two parameterizations. So what you're doing here, you have actually two submanifolds. There is a submanifold of arc lengths. There are submanifold where subset. We're not sure that they are submanifold. Nobody proved it. I just believe it. But you interpolate between this submanifold. So this specialized way to parameterize curves. Okay, so curve arc length is, instead of integrating the absolute value of the curvature, you add the length. And as I said, it takes into account the lengths that you need, it takes into account also the geometry, the distances between points. I should have mentioned that the curvature length parameterization is so I did it here for 2D. I show it for 2D, but you can do it in 3D. And so in 3D you have curvature and torsion, and you have this moving frame that's go with your curve. So you define it by the velocity, the binormal and normal. And this moving frame is a moving frame. So it's a curve on SO3. And you can compute the length of this curve in SO3 using the Killing form. And what you will get, if you renormalize this curve in SO3 by arc lengths, you will exactly end up with a curvature length parameterization of your curve. And if you take into account the starting points and not only look at the SO3 but also at the arms, so at the distance to the starting point. So now you have SO3 and a vector, and so SE3. And then if you do the same, compute the length of this curve and parameterize it by arc lengths, what you will get is a curve at arc length parameterization on the contour. So this is the link with geometry on groups. So what is to remember so far? So the only local geometric invariant of plane curves are the curvature. If you keep in mind the length function, how the length is varying. So for arc lengths, you just need the total length. That's enough, and the curvature function to recover your curve. If you have another parameterization, you need to keep in mind the length information. Any strictly increasing function applied to the absolute value of the curvature defines a canonical parameterization. So you can do exactly the same as I did. If you have a strictly increasing function, you fix an increasing function, you put as input the curvature, absolute value of the curvature. You will get automatically a diffeomorphism that you can apply to your curve and have a special canonical parameterization. And finding the right parameterization adapted to a given application is actually finding a the right strictly increasing function. So what is the right parameterization of bones? So in this example of bones, we investigate a family of parameterization. There are two parameters, C and lambda here. And so in order to recover the costly algorithm of Dodberg that is used in the hospital, the best parameters that we get are these ones. And here you probably don't see it because the two solutions are superposed. But the points are exactly at the same anatomical position. So, and this is there's no cost for this reparametrization because reparametrizing by arc lengths or by some canonical parameterization, it's 2 lines of code if you know the function. So whereas the algorithm of Dodberg it takes 10 minutes for 30 bones, so it's more costly. So this was the green part of my talk. Do you I have 2 minutes? No,
one.
-1. I have -1 minute.
No, you have 1 minute.
Let's say okay. I was interested in visualization of infinite dimension data, and these are leaves. So I extracted the contour of these leaves, and I wanted to see how these leaves, so these different leaves are placed in space, and how the parameterization of the contour is affecting the distances between the different clusters. So these are different classes. So here I had the problem to visualize it. So you can see a t-SNE of this is for arc length parameter. This is for clock parameterization. I will tell one thing about it. So here in the middle there is a visualization procedure that I used, which I called LPCA, but I think I will need to change the name. I probably have no time to explain this visualization procedure, but anyway, it helped me to understand what was wrong with arc lengths. In this setting, there was leaf with peduncles and leaf without in the same class. So arc length parameterization was very bad, because if you add some peduncle, you will really change the position of the points. And have a lot of variability in the same class. So this is a clock parameterization that I propose. So here your proposition is to parameterize with a constant angle around the contour. So this is a clock parameterization. I should do it like this, right? Anyway. And perhaps I will show a little film, less than 1 minute, hopefully. So this was for explaining the way I define the visualization, because this is an infinite dimensional manifold we want to visualize. So as I said, I called it first LPCA, but its name is already taken. So perhaps BOF is better, bouquet of flower. Anyway, let me show you what it does on so this is a procedure. You have data points with different color coming from different classes. So these are data in 3D, and what you want is to visualize them in 2D. So you connect to the mean of the data set. And then it's like you have a bouquet of flower, and then all flowers are dispatched in the same plane. And then, like if you put flower in a book. So that was just to explain the visualization. I will show you now. So here you have a contour with the sample coming from a given parameterization. And on the other hand, you have the distances or the position in 2D of the visualization of the position in 2D of all the classes. And of course, it depends on the parameterization. So yeah, you see the points moving on the left. And so the infinite dimensional manifold is also affected by the parameterization you are taking, and so it really affects the position of these points. Thank you very much for your attention. Sorry for having taken too much time.